So we'll just putting the title. So here comes the question. A parallel plate capacitor of area capital A with plate separation D, that is small d, and capacitance capital C is filled with three different dielectric materials having dielectric constants K1, K2 and K3. Okay, and K3 as shown. So you have a diagram for this question. I'm just drawing it. So this is the distance, and inside this you have the capacitor arrangements. Okay, Ingla, so this is the figure. We'll continue with the question. If a single dielectric material is to be used if a single dielectric material is to be used to have the same capacitance C in this capacitor, then its dielectric constant K is given by, so you have options. First, option A, 1 upon K is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3. And option B, 1 upon K is equal to 1 upon K1 plus K2 plus 1 upon 2 K3. Option C, K is equal to K1 K2 upon K1 plus K2 plus 2K3, and option D, K is equal to K1 times K3 upon K1 plus K3 plus K2 times K3 upon K2 plus K3. These are the options. Okay, I'll just show the question. So try solving this. So try pannunga. Tell me what are the steps that you're getting. Yes, so which of the options you feel is right?
Sir, option D.
Option B, second one.
Yes, sir.
No, it is not second one. So first in the combination first கண்டுபிடிங்க. That is the main thing.
Option C, sir.
Option C. No, that is also wrong. Let's not go with Inky Pinky Ponky. I want you guys to try it. So K1, K2 and K3. So they are in what type of combination? Is it series or is it parallel?
Parallel and series, sir.
So first one, you have to consider them to be parallel because K1 and K3, if you see, the combination is they are going to be in parallel. So first do that. For each of the portions, you try to find out what is the effective capacitance. So that is the first aspect. So you had two capacitors. So if I'm going to divide them, so this is K1 and கீழ வந்து K3 இருந்துச்சு. Isn't it? So this is how it was.
Sir, option D.
Yeah, option D is correct. Okay, the moment you see this two capacitors are there, you can easily find out. நம்ம வந்து சால்வ் கூட பண்ண தேவையில்லை. See here. So this is A by 2 இல்லையா, the area for this. இதெல்லாம் கொஸ்டின்லயே கொடுத்திருந்தாங்க. And this one was D by 2. Isn't it? This length. So all that was already mentioned. So in the Mari, how many such capacitors you have? You have two such capacitors which are there. This was K2 and this was K3. So you can imagine these two. These two together is going to make up one single capacitor whose dielectric value is going to be K. So அதோட area வந்து will be A only. Okay, and the thickness is going to be D only. So all this is known to us. இதுதான். So first aspect is this. So இந்த ஒரு analogy வந்து you will have to build up. So first finding out this. Once you have found out this, your job is done. So you understood the question. Now you can see that K1 and K3 obviously they are going to be in parallel to each other. And then overall combination you are anyways going to do a series. So first அதுதான் நீங்க வந்து பண்ணணும். So once you do that, K1 and K3 you can see that those two are in parallel. Whenever two things are in parallel, what is the formula? So it's K1 K3 upon K1 plus K3 for this. அதே மாதிரி for this it's going to be
K2
so when you
plus K2
yeah.
into K3 divided by K2 plus K3.
Correct. So series first பண்ணிடுங்க. So that is what we are doing. K2 and K3 upon K2 plus K3. And these two are going to be in parallel, isn't it? So what you do, you just go for a simple addition. So ரெண்டுமே add பண்ணணும். That's it. So you get the answer. The answer is option D. That's it. Okay, fine.
Yes,
so
sir.
questions may seem complicated, but when you break it down, it seems to be simple. Seri, we'll go to the next question. Okay, next. When n capacitors, I'll write it like this. N capacitors connected in parallel to a source of X volts, then energy stored is equal to your options. Option A, Cx. Option B, n Cx square upon 2. Option C, Cx square. And option D, Cx square upon 2n. So when capacitors are connected in parallel, then what is the energy stored in them? So n capacitors you are connecting.
Sir, option B, sir.
Option
B, sir.
Option B. Okay.
X square divided by 2.
Yes. So what is the formula for energy stored by a capacitor? It is given by U is equal to
CV square divided by 2.
Yes. So it is CV square by 2 or half into CV square. So because you have n capacitors and they are in parallel, so obviously it is going to be n times. It will be enhanced. So therefore n CV square upon 2. In this place they are replacing V with X. So it becomes NC X squared by 2. So the correct answer is option B. Okay, so this is quite easy only. So moving on to the next question. Okay, next question. Mass of a proton is 1840 times mass of a proton is 1840 times that of an electron. That of an electron, full stop. It is accelerated through a potential difference of 1 kilovolt. Okay. What is the kinetic energy associated with the proton? So your options are, first one, option A, 1 kilo electron volt. Option B, 1 upon 1840 kilo electron volt. Option C, 1840 kilo electron volt. And option D, 1 kilovolt. Okay, this is a question.
Sir, 1 kilo electron volt.
1 kilo electron volt. Okay. So what is the formula you used?
Sir, kinetic energy is equal to charge into potential difference.
Yes, kinetic energy is equal to charge into potential difference. Okay. So kinetic, it's basically an application of work energy theorem. So you will have to, show it that way. What you said is right, but it comes from the work energy theorem, because work done is equal to the change in kinetic energy. So we apply that concept, and you know that work done is nothing but the product of charge and potential difference.
1 by 2 mv square minus 1 by 2 mu square.
So yeah, you can do that, but here directly we apply it because you want to find out kinetic energy. So in the place of work done, instead of doing that, we are doing a reverse calculation. So work done can be written as W into W is V into Q, no? So அந்த ஒரு கான்செப்ட் நம்ம யூஸ் பண்றோம், product of charge and potential difference. Okay. So now what is the charge here associated by an electron? 1 kilo. Oh. 1 electron. Yeah. Yes, so just an electron we are talking about. So it's 1 electron times the potential difference is already given in the question as kilovolt. So 1 electron times kilovolt, which is 1 kilo electron volt. That's it. So the answer is 1 kilo electron volt, which is option A.
Sir, what down, sir?
Yes.
Sir, இப்போ mass of the proton நம்ம யூஸ் பண்ண மாட்டோமா சார்?
No, நம்ம யூஸ் பண்ணல. You need not use the relationship. அது வந்து it is just ஒரு ரிலேஷன் கொடுத்துருக்காங்க, அவ்வளோதான். which is a fact. ஸோ அதை நம்ம யூஸ் பண்ண தேவையில்லை. Okay. Yeah. So that's how you do this. Next question. Okay. A 10 microfarad. So I hope you know what is micro. A 10 microfarad capacitor is charged to 500 volts, and then its plates are joined together, and then its plates are joined together through a resistance of 10 ohms. Okay, through a resistance of 10 ohms. The heat dissipated by the resistor is option A 500 joules, option B 250 joules, option C 125 joules, and option D 1.25 joules. Yeah, so in a given data, அது பாருங்க. So interpret the data and then you can relate what formula you can use. So microfarad, micro na உங்களுக்கு தெரியும் நம்புற. So 10 power
10 power minus 6.
10 power
Yes.
minus 6.
ஆமா 10 power minus 6.
10 into 10 power minus 6 னு எடுத்துக்கிட்டா சார்.
ஆமா, which is 10 power minus 5 and you can simplify.
Okay sir.
Yeah.
Sir, 1.25 joule.
Yes, 1.25 joule is correct. Yes, சொல்லுங்க எப்படி பண்ணீங்க?
Sir, E is equal to CV square divided by 2, sir.
ஆமா, first வந்து அது energy தான். So energy and heat both are the same. So energy stored in the capacitor is equal to the heat produced, okay, is equal to
CV square divided by 2.
yes, half CV square or CV square by 2. சரி.
C is equal to 10 into 10 power minus 6, sir.
Yeah, 10 power minus 5 எழுதிக்கிறேன். Okay. V square.
Okay. V square is equal to 500, sir. 500 the whole square.
சரி. So 500 times 500 அப்படின்னு போட்டுக்கலாம். Okay. So what do you get here? So you cancel them out.
125 into 10 power minus 2.
25 times 5 வந்து is nothing but 125.
125 into 10 power minus 2.
So minus 5.
1.25 joule.
Minus 5 plus 3 is minus 2. That's correct. So can be expressed in scientific notation as 1.25 into, yeah, that's it. 1.25 எழுதிக்கலாம் directly. 0. Okay. Minus 2 plus 2 is becoming 0. Fine. So this is the final answer. Okay. புரிஞ்சுதுங்களா? I hope everybody it's clear. Heat dissipated is 1.25 joules. Okay. Moving on to the next one. So, fifth question. Okay, the capacity of a spherical capacitor is 1 microfarad. Full stop. If the spacing between the two spheres is 1 mm, that is 1 millimeter. The radius of the outer sphere the outer sphere is, so here goes the options. Option A, 3 centimeters. Option B, 6 centimeters. Option C, 3 meters. And option D, 6 meters. So a spherical capacitor has been given. So what do they mean by spacing between two spheres is 1 mm? அப்படின்னா என்னது? What is the meaning? சொல்லுங்க.
Sir, R2 minus R1 is equal to 1 mm.
Correct. Yeah, R2 minus R1 is 1 mm. So you can convert, you can directly write it as 10 power minus 3 meters. Yeah. And they've given you the capacitor also, capacitance value as 1 microfarad. So convert that also, which is 10 power minus 6 farad. அப்புறம் வேற என்ன கொடுத்துருக்காங்க? So these are the two datas we have.
Yes, sir.
Yeah. So what is the formula?
3 meter.
Yeah, சொல்லுங்க.
3 meters, sir.
3 meters. Okay, that's correct. But how you got it?
Sir, I used the formula C is equal to 4 pi epsilon naught into R1 R2 divided by R2 minus R1, sir.
Yeah.
Then I simplify this and R1 is equal to R1 is approximately R1 is equal to R2, sir.
So first you tell me what is the R1 R2, because you're substituting, no? 10 power minus 6 is equal to 4 pi epsilon naught R1 R2 upon 1 millimeter, which is 10 power minus 3. I suppose
Sir,
you did this.
R1 R2 approximately equal எடுத்துக்கிட்டேன் சார். நான் கம்மியான டிஃபரன்ஸ் இருக்கிறதுனால ரெண்டு ஈக்குவலா இருக்கும்.
அதுக்கு வந்து காட்டணும் இல்லையா, how it is கம்மியா இருக்கு அப்படின்னு சொல்லி. You should have some concrete evidence to show. How did you do that? That is my question.
டிஃபரன்ஸ் கம்மியா இருக்கிறதுனால.
So okay, the difference என்ன வந்துச்சு? R2 minus R1 difference
10 power minus 3, sir.
No, அது கொடுத்திருக்காங்க questionல. My question is R1 R2 value. The product we don't know. We know only the difference. Tell me what is the product? 1 by 4 pi epsilon naught அப்படிங்கிறது வந்து we know it as K, which is 10 power 9. Have you applied that?
Yes, yes, sir.
Okay, so what is R1 R2?
Sir, R1 R2 is equal to 9 into 10 power 9 into 10 power minus 9, sir. That is 9,
yes,
sir.
Correct. You will get it as 9. So what
Yes.
does that mean?
R1 into R2 is equal to 9, sir. Then the radius is very small or equal.
Radius is very small or equal. That means
Difference is very small. So R1 is equal to R2, sir.
R2 minus R1 is very small in comparison. So hence you should say that R2 is
Equal to R1.
R2 is equal to R1.
Yes, sir.
Approximately it is equal to R1. So what will be the value then if you're
R
going for
square is
this?
equal to 9, R2 is equal to 3, sir.
Yes. So you basically get R2 square is equal to 9, which means R2 value is going to be 3 meters approximately. So you go for an approximation finally. So in the Marida, we solve this type of question where you have an approximation. The product value is very less, and therefore you substitute and you get R2 is 3 meters for this question. Okay, class? So this is how you approach this. Good. So the answer is option C. Okay. So is this part clear?
Yes, sir.
All right. So next, moving on. So we have seen all aspects, I guess, in this chapter. We'll see the other capacitors. Spherical we have seen.
Yes, sir.
Okay. So shall we move on to the next chapter? Electricity.
Yes, sir.
Okay, so electricity formulas you want me to brush up, or you guys are aware about the formulas? Current electricity. Yes. சொல்லுங்க. You already know the formulas for current electricity. Yeah.
So current is equal to charge divided by time.
இல்ல I'm not asking you the formulas. My question was உங்களுக்கு formulas தெரியுமா இல்ல formula list நான் தரட்டுமா? That is my question.
Sir, கொடுத்துருங்க sir, recap.
Okay, you wanted the formula list. Okay,
Yes, sir.
fine. So we'll go from the basic formulas from top to bottom. Okay, so the first basic formula, we'll just put the heading. Okay, so first one, how can you express current? Electricity or the electric current can be expressed as the rate of flow of charges. So I is equal to Q upon, Q upon T. So here Q is nothing but charge in coulombs and T is time in seconds. Yep, I is nothing but the current in amperes. So this is the first formula. So what is the relationship between the units? You can simply say 1 ampere is equal to 1 coulomb
1 coulomb divided by
1 second, which is nothing but coulomb second inverse. Okay, so second formula, we have the electric potential. So how we can express electric potential? So V is equal to,
Work done by Coulomb.
yeah, work done upon
Charge.
charge. The ratio of work done by charge is electric potential. So W is work done in joules. Okay, and V is nothing but electric potential. What is the unit? It is volts. So we can say 1 volt is equal to 1 joule upon 1 coulomb, which is nothing but joule coulomb inverse. This is the second formula. Going to the third one. Third one is Ohm's law relationship. So according to Ohm's law, the potential difference is directly proportional to the current passing through a conductor, provided that temperature is going to remain constant. Okay.
V is equal to Ri.
Yes. So V is equal to R into I. So here V is again potential difference in volts. R is nothing but resistance. So resistance is having the units ohms, and I is as usual current in amperes. So this is the relationship. So you can say 1 volt is equal to 1 ohm times 1 ampere. So next, moving on to the fourth one. Next, you have factors affecting resistance, which is called as resistivity. We'll talk about that. So
R
R is
is equal
equal
to
to,
rho L divided by A.
yeah, rho L by A. So where rho is called resistivity of a conductor, and L is length of conductor. So length is usually in meters, and resistivity is in ohm meter. So these are the units. And A is area of cross section. So the unit for area of cross section is meter square, and resistance, as usual, it is going to be in ohms. Okay, so this is the relationship. So you can say 1 ohm is equal to 1 ohm meter times meter upon meter square. So you can see that it is same on both the sides. Next, moving on to the fifth one. The next formula. You have something called as current density. So current density is given by the letter J, small j. So J is equal to, it is the amount of current passing per unit area. So it's I upon A. Okay, so this is current density. I is again in ampere, current in amperes, and A is area in meter square. So the combined unit for current density would be ampere per meter square. Now further, how can we express this? Current can be written as the product of, I mean, Q upon T. That is what we saw in the first place. So you can write this as Q upon
Right time in the area.
yeah, A into T. So this is one more relationship that can come into picture. So further can be expressed as coulombs upon meter square and second. So this is how you can express it. Then moving on to the next part. Then you have something called as conductance. So conductance is represented by the letter G, capital G. So it is the reciprocal of resistance. So G is nothing but 1 upon R. So the reciprocal of resistance. So resistance unit is ohms. So conductance has got the unit as ohm inverse, or it is also called as Simon, or it is also called as mho, MHO. So ohm நம்ம திருப்பி போட்டோம்னா we'll get ohm, mho. Okay, so it is mho. So this is all about conductance. Then moving on. Then we have drift velocity. So drift velocity of the electrons in a conductor. So we're going to see that. So this is represented using the letter Vd. So it's electron times electric field into relaxation time tau upon m, which is again mass. So we express it like this. So where E is 1.6 times 10 raised to minus 19 coulombs. So that is the value that we would substitute while solving problems. And capital E is nothing but electric field in volt per meter. And tau is nothing but the relaxation time, or the drift time also you can say. And m is nothing but mass of the electron. So mass of electron is basically a constant. So you're aware about the values?
9.1 into 10 power minus 31 kilogram.
Yeah, minus 31 kgs. So we'll substitute that. Okay, so that is the formula for drift velocity. Same way you can also express in terms of resistivity also and resistance also. So resistance has also got a formula in terms of this. So R is equal to mass into length divided by N into E square tau A. So this is a formula in terms of resistance, where M is mass, L is length of the conductor, N is nothing but number of electrons, E is electron charge, tau is relaxation time in seconds, and A is area of cross section. This is one more formula. Then moving on. So I'm just showing you all the different combinations. Adukapra we have resistivity also in terms of mass, number of electrons. So Ne square times tau. So this is also one more formula. Okay. And 10th one, quantization of charge. So how you can express charge? Charge can be expressed as integral multiples of electrons. So you can write Q is equal to N into E, where N is integral values, Q is coulombs, and E is nothing but electrons. Multiples of electrons you are expressing. Simple. So any charge can be expressed as multiples of electron charges. Then 11th one, in terms of current, how do we express? I is equal to NEA VD. So the drift current, this is called. So where I is drift current in amperes and V is drift velocity and A is area, E is electron charge, and n is nothing but that integral value. Okay, appropriately units. Drift velocity unit would be meters per second, area would be meter square, charge would be in coulombs. Okay, appropriately we are mentioning it. And then 12th one, in terms of current density, how do we write? J is equal to Ne times Vd. So where J is current density, and E and Vd already you know it, so I'm not repeating that. And then 13th one, how can you express electric field and current density? An important expression. E is equal to rho times J. Okay, so where E is electric field in volt per meter and rho is resistivity, the unit is ohm meter, and J is current density, which is ampere per meter square. So this is also an important relation. Moving on to the next one. Next, temperature coefficient of resistance is what we are seeing next. So it's basically the change in resistance per original resistance when you raise the temperature by 1 degree. When temperature is raised by 1 degree, what is the change in resistance to original resistance? That's called the temperature coefficient of resistance. It's given by the Greek letter alpha. So alpha is equal to R2 minus R1 upon R1 times T2 minus T1. Okay, where T1 and T2 is not time, it is the temperature. If you want, you can use capitals. Okay, don't get confused here. So T2 minus T1, where they are, T is nothing but the temperatures. Okay, so can also be expressed as delta R upon R1 times delta T. Okay, so this is how you express it. So the unit of temperature is degree Celsius. The unit of resistance, you know, it's already ohms. Okay, so what was the unit of alpha? It is degree Celsius inverse.
1 day.
Okay, Celsius inverse அப்படின்னு சொல்லலாம் because it is in the denominator. அதனால. Next, electron mobility. So we are seeing electron mobility. It's given by the letter mu. It is basically the drift velocity required in a unit electric field. The amount of drift velocity required by an electron in a unit electric field is called electron mobility. So it's given by mu, which is the ratio of drift velocity and electric field. So you can be written as Vd upon E, which can further be expressed as Q times tau upon M. So this is the formula for electron mobility. The unit for Vd is meters per second. For electric field, it is volt per meter. For Q, it is C, that is coulombs. For time, seconds. And for mass, it is going to be kilograms. So appropriately, you can express. The standard unit for electron mobility can be expressed as, so you have meters per second. just take the reciprocal of the electric field. So it's meter square, second inverse, volt inverse. Can be expressed like that. Then moving on. Relation between mobility and electric current. So we'll see that also. So we know that current I is equal to, in terms of, okay, drift velocity, you go and substitute. So you will get E N A mu times capital E, which is the electric field. So where E is electron charge, N is an integral number, A is area of cross section, mu is mobility, and E is nothing but the electric field. So we can express it like this. So this one is the relation between mu and I. That's mobility and current. And then combination of resistors. So resistors are having two different combinations. What are they?
Series and pair.
Yes. So you have series and parallel combination. In series, the resistors are connected one after the other.
R is equal to R1, R2, R3 plus dot dot.
Yes. In parallel, the resistors are connected one below
1
the
by
other.
R is equal to 1 by R1 plus 1 by R2 plus 1 by R3.
Yeah. So now if you see the circuits, the current flowing through resistors in series combination is same. So in series combination, it's very important to understand that current flowing through each resistor is the same. Okay, but in parallel, if you see, the current will not
Potential
be same.
difference is same.
Yeah, in parallel, it is the opposite. Current flowing in each resistor is different. Yeah, now it is branching, no? So current will get split. So here current flowing through each resistor is different. Now this may not be, same all the time. If resistors are same, then it might be, equal amount of current that is going to get divided. Okay, that is only if that condition applies. If it is going to be like type of resistors or similar resistors. If you have non-similar resistors being connected, it's going to be different anyways. So that's one aspect. And the second point is potential difference. For series combination, the potential difference is always different, okay, for each resistor. It's different across each resistor, but in parallel combination, potential difference is same. It is same across each resistor. So that is again something that you will have to note down. Now going to the formulas for effective resistance in series, you can write Rs is equal to R1 plus R2, so on up to Rn. So you can use summation operator for this. So you can say sigma I is equal to 1 to n Ri. Okay. Same way for parallel, you just need to take reciprocal of that series. You will get parallel. So 1 upon Rp is equal to 1 upon R1 plus 1 upon R2, so on up to 1 upon Rn. So again, you can express this in terms of summation 2. So it's sigma I is equal to 1 to n, 1 upon Ri. You can express it like this in terms of summation. Okay. That's all about series and parallel combination of resistors. Okay.
Yes, sir.
Yeah. After this, we have what is the current bifurcation or current division in resistors when they are connected in parallel. So there is a formula where you can directly find out. Moving on to that. This is the division of current in resistors connected in parallel. So imagine you have two resistors like this. So let's take this as R1, this resistance as R2, suppose. Yeah, and here you can see that there is a node or a junction at point A. So the incoming current, I will take it as I. So when current enters the junction or a node, so what is a junction or a node basically? That is a point where two or more resistors meet. You call that as a junction. Okay, so 2 to 3 resistors or 3 wires are meeting here basically. So 3 or more resistors when they meet, you call that as a junction or a node. So the current which is entering the node or the junction here, I, is going to get split as I1 and I2. So we wish to find out what is I1 and what is I2 in terms of incoming current, okay, and the resistors. So you can write I1 as
R1 into V.
R2 upon R1 plus R2 into I. This is the formula. Okay. This is for I1. Same way, I2 can be written as R1 time R1 upon R1 plus R2 into I. This is called as a current divider. We are trying to divide the current and then write down the formula. Okay. That's it. So these are the formulas for the incoming, for the currents in the resistors, distribution of currents in the resistors when they are connected in parallel. Okay, so this is very useful for you to solve the questions whenever you have a circuit or in between the circuits. When you can see the two resistors are in parallel, you can find out accurately what is the current flowing in each one of them. Okay, even without using the laws, directly in one step you can do it. And moving on to the next one. The next formula, the internal resistance of a cell. So we'll see the relation between EMF E. So E is nothing but EMF, that's electromotive force, potential difference, that is terminal potential difference, V, and internal resistance, internal resistance small r. Okay, so we'll see the relationship. So here if you see the internal resistance small r, so I'm just representing this. So in reality the cells and batteries that we use, they all have a small amount of resistance. So therefore the EMF is given by E. Terminal potential difference is given as V. So the potential across this resistor, we take it as V. And this one is small r. Okay. So in that case, we can express this as this is positive and this is negative terminal. Okay. This we'll take it as capital R. You know how the current is going to flow. It flows anti-clockwise in this circuit the way I have drawn it. So here we apply some law called as the Kirchhoff's laws. Okay, so when you apply it, what happens here? When you go in the direction of current, you take it as positive. When you touch the negative terminal of the cell or the battery, you take the sign convention as negative. So these are the important rules that you apply. So we'll apply the loop law. We are moving inside the loop. So I into R plus I into small r minus E is equal to 0. So sum of the potentials inside a closed loop is always equal to 0. That is what I have applied. You go for a rearrangement, you will get E is equal to I times capital R plus small r. Okay, so you get it like this. So therefore, if you rearrange it for current, you get I is equal to E upon capital R plus small r. So this is how you get the relationship. Okay, simple. So maximum current can flow through the cell if your resistance is going to be disengaged. So the maximum current I max will be equal to simply E upon small r. So when you remove the load resistance, so that is a condition for maximum current. So these are the important things that you will have to know. Same way you can write it for internal resistance also. The formula, it will be E minus V upon I. So just I went, you do a rearrangement and simplify it, you will get this. So this is another formula. Okay, simple. So this is the 19th one, and then 20th. Cells in parallel. So parallel combination of cells. So you can write the current I is equal to M into E upon M into R plus small r. Okay, so here where M is nothing but number of cells. That's it. We are just trying to generalize it. So these are the cells in parallel combination. Same way you can express the cells in series also. So you can write that as equal to N into E upon R plus NR. Where here small n represents the number of cells. So like this we can express it. And then you have the Joule's law of heating. according to this law, the heat produced is equal to, usually we can express heat as the product of power into time. And then you go and apply for power. P can be expressed as a product of potential difference into current into time. So VIT. Now from Ohm's law, you substitute for V in terms of IR. So you get I square R into T. Now for I next you substitute, you will get V square upon R into T. So these are all the combinations of formulas which are possible. Okay, so for power, you can express power as the rate of doing work done upon time. You know that work done can be expressed as charge into potential difference, isn't it? So charge by time can be expressed as current. So you can write it as V into I, and that's how we got the relationship. All right. So P is equal to VI. That's what you go and substitute here. And then you substitute for Ohm's law, you get the other relationships. That's quite understandable. So this is Joule's law of heating, and obviously heat is in joules, power is in watts or watts, and time is in seconds. Okay. Simple. So this is the formula. Next, moving on. So the formulas for electric power, same way as I already told, V into I, which is I square into R, and V square upon R. So these are the formulas. You just rearrange them in terms of Ohm's law, you get the others. Okay. The unit is watts. So the next one, the electrical energy. So electrical energy can be expressed, again, energy as a product of power into time. Okay. Likewise, how we did it for heat, it's basically the same. So again, energy would be in joules, power would be in watts, and time would be in seconds. In this electrical energy, we have something called as commercial unit of energy. So the commercial unit of energy is expressed in terms of kilowatt hour. So the amount of, the number of kilowatts of electricity that we use every hour, based on that we get a monthly electricity, consumption. So that's kilowatt hour. So you can simply express 1 kilowatt hour as, that kilo is 10 to the power 3 or 1000. So 1000 watt hours. You can convert hours in terms of seconds. You will get 10 power 3. So 1 hour has got how many seconds? 3600 seconds, isn't it? So now it's got converted to watt seconds. So can be expressed as 36 into 10 to the power 5 watt second. Further, you can express in scientific notation as 3.6 into 10 to the power 6. It becomes joules, because 1 watt second can be expressed in terms of joules. Okay, because work done into time or energy into time is basically expressed as energy. So the energy unit is again joules. So 1 kilowatt hour, the equivalent is 3.6 into 10 power 6 joules. So this relation is quite important. So this is all about the electrical energy. And power consumed by appliances. Next, we are seeing power consumed by appliances connected Okay, power consumed by the appliance is connected in parallel combination. So whenever you have n number of appliances connected in parallel, then the power consumed by all of them together can be written as P is equal to P1 plus P2. It goes on until Pn. Can be expressed in summation as sigma I is equal to 1 to n Pi. Okay, so this is the power consumed, total power consumed by appliances connected in parallel. Same way, when they are connected in series, it's the other way around. So power consumed when appliances are connected in series. So when they are connected in series, just the reciprocal needs to be done. 1 upon P is equal to 1 upon P1 plus 1 upon P2, so on up to 1 upon Pn. Can be expressed in summation also as sigma I is equal to 1 to n 1 upon Pi. Okay, so this is how we can express. And then we have efficiency. So next we have the efficiency of electric device. So the efficiency is given by the Greek alphabet eta, wherein eta can be expressed as the ratio of output power to input power. So you can say power output upon the power input. So you can express it like this. So the same way you can also calculate percentage just by multiplying it with 100. So you get the percentage also. Then we have the Kirchhoff's laws. So here you have two different categories.
Manish, we can close a bit early today because of the Pongal.
Okay.
No? Maybe
Okay,
another
okay.
another 5-10 minutes we'll close.
Okay, we'll wind up. Yeah. So Kirchhoff's laws. Just we are done, children. Almost we are coming to an end. Just another 5 formulas are there. So after that, so that you will get the complete formula list, you can prepare. So next class we can see all the questions and finish this also. So the Kirchhoff's laws, we have two different laws here. So Kirchhoff's current law, which is KCL, and Kirchhoff's voltage law. Okay, so the Kirchhoff's current laws gives you the relationship as the sum of the currents entering, or you can say sum of all the currents entering or leaving the junction is going to be equal. So we can simply say sigma I is going to be 0, or incoming currents would be equal to the outgoing currents. Same way for Kirchhoff's voltage law, sum of the potentials in a closed loop is going to be 0. So sigma V is going to be 0. So you can express like that. So that's about the Kirchhoff's laws. And then we have the potential gradient of a potentiometer. So it's given as K is equal to V upon L. So V is potential, the potential difference in volts, and L is length of the potentiometer wire. So the units would be volt per meter, as you can see. And then comparison of EMFs of two cells. So we can compare the EMFs of two cells as E1 upon E2 or in terms of E2 upon E1. So the EMF of the second cell with respect to the EMF of the first cell can be written as L2 upon L1. This is a simple comparison. Then you have Wheatstone bridge condition. So where P by Q is equal to R by S, where P, Q, R, S are four resistors connected, in the shape of a Wheatstone bridge, like this. And you have a galvanometer in between. The cell with potential V is connected. So you have P, Q, R, and S. So this is a Wheatstone bridge balancing condition. So here G is your galvanometer. So under balanced condition, the galvanometer wouldn't show any deflection. That's basically, the pointer would point out 0. Okay. That's it. So with this, we come to the end of all the concepts which are involved in this chapter, current electricity. Okay. So in the next class, we can see the numericals. Okay. Yeah.
Thank you, Manish.
Yeah. Welcome.